In the previous video, we took a look at series circuits involving a resistor and an inductor. Here I'd like to take a look at the special circuit of an inductor in series with a capacitor. This will come back later because this turns out that this is basically an experiment due to Heinrich Hertz, as in the person who later became the unit. And so we will be revisiting this circuit. So at the moment I just have an inductor and a capacitor, and somehow I have to get it charged. So for the moment we will just imagine that Scotty beamed the charges on here. So initially we'll place plus Q here, and initially we'll place minus Q here. So as a pause and ponder for you here, I want you to think about what will happen after I put the charges on the plates. What, if anything, is going to happen next, and try to come up with as complete of a description of that as possible. All right, so what's going to happen is actually quite a bit. Initially here, the inductor doesn't have any current going through it, so there's no back EMF. The capacitor then is effectively shorted out, which means that's very happily going to want to start discharging. So let's go ahead and just start by drawing this initial situation here. And we'll just draw some big plus signs to indicate that, some big minus signs to indicate that. And so because we've got a voltage across the capacitor, we will be able to drive a current going through the circuit. So that is indeed what happens. So let's go ahead and think about the next frame of this. Oops. Okay, and let's actually give this a few more charges. There we go. So now this is going to start discharging, and while it's discharging, we're also going to be driving a current through the circuit that is running counterclockwise. So now eventually we're going to get to a point where the capacitor is completely discharged. So what do we have happen there? Are we done? Well, no, because remember, the inductor will keep doing whatever it can to keep the current flowing. So that is indeed what will happen, is we will still continue to flow current even though the capacitor is discharged. So that's going to have an effect of charging the capacitor, but the other way. So as the current continues to flow, we start putting charge on the capacitor the other way. There we go. And then finally, this whole sleigh ride is going to come to a stop at some point. with our capacitor holding as much charge as it possibly can, but now with the opposite sign. So what's going to happen after that? Well, it's the exact same thing we had happen here, except the other way. So we're going to end up, So we're going to end up now starting to run a current the other way through the circuit like so. So the capacitor will be starting to discharge as that happens. And then we will get to a point where the capacitor is fully discharged. But since inductor will always keep, we'll endeavor to keep the current a constant, we'll still have a current at this point. Oops. And that current continuing to run will start charging the capacitor the other way. So again, we will be left with starting to put positives up here. And then finally, we're going to get to a point where the capacitor is fully charged. Oh, wait, we've seen that one before. Oops. There we go. And the process starts all over again. So, the question is where is the energy coming from to keep this process going? Well, we remember that initially, if I have a charged capacitor, I am storing energy because I have built an electric field. As the capacitor discharges, the electric field is collapsing, but that increases the current going through the inductor. So we will start to build a magnetic field in the inductor. Let's say it's oriented like that. I don't know which way the windings are going. Then here, when it's completely collapsed, this is when we will have gotten, the electric field is completely collapsed. This is when we will have gotten our magnetic field as big as we possibly can. Now, the magnetic field is going to start collapsing, and by Faraday's law of induction, that's what's going to keep driving the current in the circuit. So here, our magnetic field starts to collapse, and then while we are now building an electric field, pointing the other way here, and here we have a fully collapsed magnetic field, and we have put everything into the electric field. Then here, the electric field starting to collapse, because we're now driving a current, we are now running a magnetic field the other way through the circuit. And at this point of maximum discharge is when we'll have a maximum current. Looking something like that. And then finally, in this step here, the magnetic field is starting to collapse. And as it's collapsing, we're producing a back EMF to keep the current going through. And we are starting to build up our electric field again. Oops, pointing the wrong way. Starting to build our electric field again. And then we end up back where we started. So if we follow this along, we can take a look at our energy budget, if you will. So here, the energy is entirely electric potential energy. And then say here, if we look at our energy budget, the energy is entirely magnetic potential energy. Oops. What about at some point in between? Well, at some point in between, since energy's got to be conserved, if this is our energy budget here, say at the midpoint, it's half electric potential and half magnetic potential. And we can keep doing this all the way through. And what you see is we just keep transforming back and forth between electric and magnetic potential energy as we go through this process. Now this should start to be raising some alarm bells for you. Ask yourself, have you seen something analogous to this when you were looking at, when you were studying mechanics? Pause the video and see if there's anything that kind of comes to mind for you. Okay, so I'm hoping that maybe you start to think that maybe this is looking like a mass on a spring, kind of. And that analogy is actually a really good one. And we'll get into, and that's because this is going, this energy here is going as Q squared here, and the magnetic energy is going as I squared. But remember that I is dq dt. So if you think about a mass on a spring, the potential energy was going to the elastic potential energy was going as x squared, and the kinetic energy was going as v squared. So you might start to suspect that this is a simple harmonic oscillator kind of a situation here, and you would actually be correct. This is a completely analogous situation. We can make the identification fact of the spring constant being 1 over the capacitance and the mass being the inductance. And in fact, before the advent of good computers that could run really fast, sometimes engineers would actually build circuits that would mimic what, say, suspension systems would be doing or something like that, in order to get some idea of how they would behave. So we can suspect that this is a simple harmonic oscillator, but it would probably be best if we just go ahead and set up Kirchhoffs Loop Law for this and see what we get. So let's go ahead and set up Kirchhoffs Loop Law here. So we'll go ahead and take a look at the moment where we had positive charge there, negative charge there, so plus Q minus Q, and we were driving a current I through like that. So we can again go ahead and imagine walking our imaginary dog around. And so we would be going against the current. So we would write plus IR, and we would be going, sorry, not minus, sorry. We'd be writing, we are going against the current, so we'd be writing plus L di dt, and then we'd be writing minus Q over C, minus L di dt plus Q over C equals, or minus Q over C equals 0. Yeah, minus L di dt. So then we can write this as L di dt is equal, oops, no, sorry, I had it right the first time, my bad. So L di dt is equal to Q over C. Di dt is equal to 1 over LC times Q. Now, I here is equal to minus dq dt. This is because our capacitor is discharging, so dq dt is negative. So in order to have a positive current, I need this to be minus dq dt. So this will be so I'm going to observe then that this is minus d squared I dt squared. Sorry, not I, Q now. And then if I rearrange it just the tiniest little bit, we will have d squared Q dt squared equals minus 1 over LC times Q. And now our simple harmonic motion alarm bells should be going off full tilt. Remember, the prototype of recognizing that you have a simple harmonic oscillator from our studies in mechanics was that if you had something that looked of the form second derivative of stuff equals minus crap times stuff, you have a simple harmonic oscillator with the angular frequency being equal to the square root of the crap. Although since there's a 1 in the numerator, people usually just write it like 1 over root LC here because the root of 1 is 1. So this is just recognizing the form. For instance, just as a quick refresher of this, just for comparison, we can say recall, oops, here, let's do this. Say recall, say for a mass on a spring. Okay, so say this is the equilibrium position, and then we say that this distance here is x. The force on the spring was minus kx because it was displaced to the right of equilibrium. The force needed to be to the left, so a minus sign. And if it was displaced to the left of equilibrium, x was negative, so minus kx would make the force point to the right. Either way, we're good. But by Newton's second law, this is equal to ma. Whoops, ma. So we can write this as a is equal to minus k over m times x, and then we remember that the acceleration is the second derivative of position, so d squared x dt squared equals minus k over m times x. So again, it was the same deal here. Second derivative of stuff equals minus crap times stuff, which means that the crap here, k over m in this case, we identified as omega squared. So it's exactly the same thing here. The charges are sloshing back and forth in as a simple harmonic oscillator. So this is actually a way that you can make yourself a crude FM crude radio receiver. So, for instance, let's say you wanted to listen to, I don't know, let's say CIMX, its frequency is 88.7 megahertz. A typical inductor that you might put into such a circuit would have an inductance of, say, maybe something on the order of 0.12 millihenries. Inductor be on the order of 1.2 millihenries. So then we can ask ourselves, what capacitance would we need to tune the station? Well, we can say that 1 over root, that that omega, the natural frequency, which is 2 pi f, would be 1 over root, 1 over root LC. So if we want to solve for the capacitance, let's see, that's going to give me 4 pi squared f squared equals 1 over LC. I want the capacitance, so C is going to be equal to 1 over 4 pi squared f squared L. All right, well, let's go ahead and put in our numbers here. So this will be 1 over 4 pi squared. Our frequency is 8.7 megahertz, so remember you'll have to take that to hertz. And our inductance we said is 0.12 millihenries, so you'll have to take that to henries. So it'll be times 10 to the negative 3 henries. Okay, if you crunch the numbers through, you get something on the order of 2.68 times 10 to the negative 14 farads, which is a couple hundredths of a picofarad, which doesn't seem like a whole heck of a lot. However, it's actually reasonably plausible. I remember that as a kid, I got a chance to dissect my grandma's old transistor radio that wasn't working anymore, back when transistor radios were really cool. Anyway, it turned out that the tuning circuit for it had a knob. The tuning knob itself was actually a very cleverly designed capacitor. What you did, so I'm going to indicate here, this is the knob. There was a metal plate here and here. And then sandwiched between the metal plate was a thin sheet of plastic. Now on the knob was attached a machine screw. Let's make it red here. There's a little machine screw that the knob would turn. And then there was a threaded assembly here. So by turning the knob, what you did was you either made the plastic a little thicker or a little thinner. Well, the area of those plates was basically next to nothing. So the capacitance was indeed quite low. And so a couple hundredths of a picofarad is actually a very reasonable value. All right. So before we go here, I do have one little challenge question. This may have occurred to you when we were looking at this little sequence of events. I pointed out that this is a simple harmonic oscillator, and the way it was going, it looks like it's just plain going to run forever. Now we know with a mass on a spring, you have air resistance and friction, and even if you say, change it to a vertical spring so you can get rid of the friction, and you put it in an evacuated container, you're still doing some work deformation on the spring, so you're heating up the spring, so eventually, and the spring will radiate off that heat. So eventually, possibly after a very long time, that system will come to a halt. And we need it to come to a halt. Because remember, the second law, one way to state the second law of thermodynamics is that it's impossible to build a perpetual motion machine of the second kind. Remember, a perpetual motion machine of the first kind was a machine that ran forever and did useful work. It violated both the first and second laws of thermodynamics. A perpetual motion machine of the second kind merely violates the second law of thermodynamics by getting rid of the stipulation doing useful work and saying that the thing will just plain run forever. So how are we going to get energy to leak out of this system? Remember, superconducting materials really are a thing. So it is entirely possible to build this entire apparatus out of superconducting materials to get rid of all resistive losses. Okay, we're going to have to keep the thing bathed in liquid nitrogen to make, or say liquid helium to make that happen. So it's insanely expensive, and we probably wouldn't bother doing it. But it is a thing. So it's possible for us to build this circuit with zero resistance. So you're not going to lose energy from resistance. So if we take that out of consideration, can you imagine any other way that this could be losing energy? Pause the video and see what you come up with. Okay, so the idea here, or at least a starting point, is to recall that with Faraday's law of induction, we created electric field lines that were oriented as circles around our varying magnetic field and perpendicular to those lines. And then we also observed that those electric field lines weren't contained anywhere. They had to extend out everywhere. So this means that you are creating an electric field not just in the immediate vicinity of the coil in the inductor, but literally everywhere. That's going to be doing work on other charges out in other places. And in fact, when we follow this through a little more in upcoming videos, what we'll be seeing is that the time-varying magnetic field will make an electric field, and if we follow this through, we'll realize that the electric field itself has to be time-varying. Now, we haven't demonstrated this part yet, but it's also a case that time-varying electric fields will make magnetic fields. In this case, they would have to be time-varying as well. And it turns out that this sort of symbiotic relationship between the time-varying electric field making a time-varying magnetic field and vice versa is what is behind making an electromagnetic wave. So not only was this thing acting as a radio receiver, but it can also act as a radio transmitter. And that is indeed what Hertz was doing, was he had constructed the first device to transmit electromagnetic waves. So we will be revisiting this circuit a little bit later when we take a look at what Hertz was doing with that. But this is the mechanism by which energy is going to leak out of the system. We're going to be propagating out electromagnetic waves through all of space. That energy had to come from somewhere, and it came from the electric and magnetic fields that were stored in the circuit. So in the next video series, we will indeed be pursuing electromagnetic waves. So I'll catch you over there.